Hello and welcome to another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 11cc, Lesson 8 on data distribution shapes. Man, does that sound technical. And yet it's really not. What we're going to be looking at today is how the data can kind of spread itself out, graphically, either in a dot plot or in a histogram. We also want to talk about some key features of data distribution shapes and how to think about them, and also what they tell us about the answer to a statistical question. So let's get right into it right away. Data can be distributed, i.e. spread out. That's what it means for data to be distributed, how it's spread out between the smallest and the largest values in many different ways. The way the data is distributed is called its shape. It's a nice kind of name for it, right? Because this data, right, on this dot plot's got a shape, right? And that shape, right, the way the data is distributed, its shape can help answer our statistical questions. So let's look at one particular distribution in exercise number 1. Camilla has her 20 classmates, including herself, pick a number at random from 1 to 10. She collects their responses and displays them in the dot plot below. A uniform distribution is one where all the data values show up the same amount of times. Why do you think this distribution is close to uniform? All right, now again, let me be very clear. This is not a perfectly uniform distribution, right? There are 10 choices and there were 20 people that chose numbers between 1 and 10. Right? So if it was a perfectly uniform distribution, we would have had 2 people choose 1, 2 people choose 2, 2 people choose 3, 2 people choose 4, etc. And by the way, that would be an amazing coincidence if that actually happened. So this isn't a uniform distribution, but it's close to uniform. Why do you think that is? Pause the video now. Well, it's pretty simple. If the students are really kind of choosing numbers at random, right? If they're just like, 7 or 3 or 8, right? If people are just choosing numbers at random, then any number is as likely to be chosen as any other number, right? So any number is as likely to be chosen as any other number. So we would expect around 2 data points per number, right? Given that we have 10, right, 10 numbers that they could have chosen and there were 20 people choosing, right, we would expect around 2 per number. Now, whether or not this distribution really would have turned out to be close to uniform is more of a question, right? Maybe people are more likely to choose a number like 7, lucky number 7. Maybe they're less likely to choose like the number 4 because it's the number 4. I don't know. Maybe a lot of people are like, I'm choosing 10 because that's what I am. Or maybe people would be choosing the number 1 because they're number 1. I don't know, you know what I mean? It's actually kind of a cool one to try ourselves. Now, this is of course tricky. If you're at home working by yourself, there is almost no way to do this. You'd actually have to probably round up like 20 people to do it. But assuming that you're in a classroom, let's talk about exercise number 2. Try the above experiment in your own class. If you have enough people, it doesn't have to be 20. Each person should pick a number between 1 and 10. I would suggest having them write it down on a little piece of paper. Collect the data and display the results below. All right, so let's back out of this for a second. This is really kind of a fun experiment, right? And it doesn't matter whether you have 10 people or 20 people or 30 people, although it does work better with a larger number of people, because if you only have 10 or 9 or 8 or something, it doesn't work nearly as well. So what I'd like you to do is pause the video now. This is going to actually take a little while. If you're working in a classroom of 6th graders, pause the video right now, especially if you're the teacher. Have every kid write down a number between 1 and 10 on a piece of paper, and don't have them consult their neighbors, because if they turn to their neighbor and say, hey, what'd you pick? I picked 5. That's a great choice. I'll write down 5, right? That's not what we want. We want kind of these independent picks to see what we have. Pause the video now and go ahead and actually do this. All right, well, I know exactly what results you got, so I'm just gonna, actually I can't, right? There's no way for me to know what results you got. So what I did is I actually kind of simulated this myself, and these are the results that I got, okay? So when I asked 20 people to pick a number between 1 and 10, this is what we got, all right? Now, the reason I like to have this is that we can then talk about some additional terminology that is associated with data distribution. Now, your answers to these are likely to be different, okay? If you are sitting at home though, and you couldn't do this experiment, what I would suggest doing is actually drawing out the dot plot that I have and then answering the questions as I do. In fact, how about this? Why don't you pause the video right now, only if you need to, pause the video right now and copy down my dot plot if you weren't able to do this experiment because maybe you're doing remote learning from home and you're doing this all on your own. So pause the video now and take a moment to actually copy down my results if you need to. All right, great. And again, I prefer that you're working with your own results, but if you're working with mine, let's talk about this. Letter A, were there any peaks in the results? Those are data values that occur many times compared to the other, right? Now, that could be the mode, right? Or there could be multiple peaks, and they don't all have to be kind of the same. For me, at least, the only one that is definitively a peak here is 7, right? We're kind of expecting 2 on each one, right? If they all got the same, if it was a uniform distribution, we'd have 2 1s, 2 2s, 2 3s, 2 4s, what we talked about in the last lesson, right? Or in the last exercise, sorry. For us though, 7 got 5 of them. So there's a peak at 7. So peaks are just simply data values that occur many times compared to the others. The mode is almost always a peak unless, the mode is like not interesting because maybe it has just 1 more than all the rest or something like that. But there's definitely a peak at 7. Also interesting, almost the opposite of peak, is what we see in letter B. Were there any gaps in the result? Those are values that were omitted or occurred a very small number of times compared to the others. All right, and for us, let's just talk about values that were omitted. So we seem to have a gap at 3 and 4. Nobody in my simulation picked either the number 3 or the number 4. Maybe it's because they're boring or, I don't know. But we've got a gap at 3 and 4. Now, the reason that we like to talk about peaks and gaps is that they can often tell us something about the answer to the statistical question that we're trying to answer. Now here, this statistical question, might have been something like, if people randomly choose numbers between 1 and 10, what numbers do they choose? Right? That would be the statistical question. What numbers do they choose? Because obviously they choose different numbers. The answer might be, well, many people will pick 7, and very few people will pick 3 and 4. Right? So peaks and gaps can help you answer statistical questions in a very similar way that things like measures of center can help you do, and even things like the range can help you answer. So let's keep looking at different data distribution shapes. Exercise number 3. The dot plot shown below shows the results of asking 30 8th grade students how many pictures they had posted to social media websites in the last week. Letter A. Where does the peak of this distribution occur? And letter B, are there any gaps? All right, great. So since we've already talked about peaks and gaps, I'd like you to pause the video right now and try to answer these 2 questions on your own. All right, Well, we've got a nice peak there around 5 media posts, right? So 5 posts. All right. We also see that there's a gap here from 12, 13, and 14. So we have a gap from 12 to 14 posts. All right. And again, that might tell us something, right? It might tell us that there's some kind of like certain number of posts that like people just don't make, you know? It also tells us that, yeah, a lot of people, right, maybe post 5 pictures per week to social media. All right. Peaks and gaps. Pretty easy idea, I think. Let's keep going. Exercise number 4. A total of 55 people were asked how many first cousins they had. The distribution of the results is shown below. Letter A, explain why we would call this a symmetric distribution. All right, so let's talk about this a little bit. The first type of distribution that we saw today was a uniform distribution. And that is what we would have seen if every single one of these was the same. So, you know, there were this many people that had 0, this many that had 1, this many that had 2, and all those numbers were the same. In other words, all these dots kind of were at the same level, right? But then we also have things called symmetric distributions, and they're really key. Because in a symmetric distribution, the mean and the median are pretty much the same value. All right, so when we see a symmetric distribution, whether we use the mean or the median to talk about the central value doesn't really matter. All right, so why do you call, what is it? What is symmetry, right? What does it mean for something to be symmetric? Pause the video now and see if you can answer something right here. All right, well, you've played around a little bit with symmetric things and symmetry, right? Symmetry really kind of means, in a very basic way, that something looks the same on the left as it does on the right, or on the top as it does on the bottom, right? It's about how it looks. In particular, right, the left-hand side of this distribution basically looks just like the right-hand side. And that's what it means to be symmetric. The left and right sides of the distribution look the same. Just fit it in. The left and right sides of the distribution look the same. And again, one of the wonderful things about symmetric distributions, you know, distributions that kind of look like this, is that whether you use the mean or the median, they're going to roughly be the same. In a perfectly symmetric distribution, like it's perfectly symmetrical, which this one actually is, the mean and the median would be exactly the same number. Anyway, letter B. What value is the distribution symmetric about? In other words, what is that middle value? You know, this is going to be both the mean and the median, right? What is the value that this is symmetric about? Pause the video now. All right. Well, it's kind of like if I were to draw a vertical line and say, well, I'm going to look at the left of this and look to the right of this. From your perspective, look to the right of this and look to the left of this, right? Then what would that value be? And that would be right here, right? If I literally look at everything on this side and I look at everything on this side, they look identical. And what is that value? 6, 7, 8, right? That is 8 first cousins. All right, and finally, right, what does this distribution suggest about the number of first cousins a person typically has? Right, and again, this gets back to all about answering that statistical question. If the statistical question was, how many first cousins do people have? Right? I mean, I've got 6 myself. You know, some people have tons and tons of first cousins. Some people have very, very few, right? What does this distribution suggest about the number of first cousins that a person typically has? Well, you know, you can say, right, that really, it's somewhere in here, right? It's somewhere, let's say, between 5 and 11. You know, right? So there's very few people that have a lot of first cousins, and there's very few people that have very few first cousins, right? Typically, a person will have a first cousin somewhere in this range. And again, nothing magical about 5 and 11. You could have even said, this distribution suggests that very few people have lots of first cousins, and very few people have very few first cousins. That would be also a great way to answer this particular question. All right, let's take a look at one last exercise. The gas mileage of a vehicle is the ratio of how many miles can be driven per gallon of gasoline used. Heavier vehicles like trucks get lower gas mileage. Lighter vehicles get much better gas mileage, and hybrids, part gas and part electric, get exceptionally good mileage. A survey of the gas mileage of 200 vehicles of all types is shown in the histogram below. Letter A, why do you think there are 2 peaks to this distribution? All right, and just to be very clear, we had been looking at peaks and gaps in terms of dot plots. There's one peak right here, right, for vehicles that get between 10 and 14 miles per gallon. And then there's another peak right here for vehicles that get between 30 and 34 miles per gallon. Why do you think there's 2 peaks? Pause the video now and maybe write something down. Statistics is all about context, all right? Many other fields of mathematics, you kind of have a context, but then you try to strip that context away and answer questions purely with math. Statistics is almost the opposite. In order to answer this question about the mathematical display of data, we have to think about the context, which was that we took a survey, right, of 200 vehicles that included both trucks that get kind of bad miles per gallon and cars that get pretty much good miles per gallon. So we likely have 2 peaks because this peak is likely for the trucks and this peak is likely for the cars, right? So one peak is for the trucks. Hello, red. One peak is for the trucks. And one peak for the cars. Right? Kind of makes sense. Now, letter B. Are there any noticeable gaps? Well, are there any noticeable gaps? And if so, where? Pause the video now and write something down. Yeah, you bet, right? Right here. There are absolutely no vehicles in the 20 to 24 mile per gallon category. And really, honestly, from a real world perspective, that's because there are very few trucks that will get as high of this gas mileage, i.e. getting between 20 and 24 miles per gallon. And there are very few cars that get this low of a gas mileage, right? So there's this gap, right? Yes, from 20 to 24 miles per gallon. Yes, there we go. Yeah. And again, gaps are easy to spot. Is there a place where there's no histogram? You wouldn't necessarily want to call this a gap, 0 to 4, right? It just simply means, there's nothing to the left. You also wouldn't want to talk about gaps that are to the right of here, right? Gaps have to be like between data, right? So there's a cluster of data here, a cluster of data here for the trucks, and there's probably some cars mixed in here. Then there's a cluster of data here for the cars, and there could be maybe a hybrid truck sitting over here as well. And then there's this gap in between them. All right, let's take a look at letter C. The highest frequency occurs in the interval 30 to 34 miles per gallon. What percent, that's a percent question, what percent of the 200 observations fell into this category? All right, I know it's been a few units since we've done percent, but see if you can figure out what percent of all the cars, shouldn't say cars, what percent of all the vehicles fall into the category 30 to 34 miles per gallon. Pause the video now and see if you can remember how to find the percent that a part represents of the whole. All right, well first, let's figure out how many vehicles even fall into that category, right? We're talking about this particular bar, and if I look over, it's a little bit hard to read, but I find, right, if I just sort of draw my line over, that there are 42, right? So 42 out of the 200 vehicles, 42 out of the 200 vehicles, right, lie in that category. But remember, what percent really is a ratio out of 100. A ratio out of 100. Currently, our ratio is out of 200. All we have to do is create an equivalent ratio that's out of 100. That's pretty easy to do because I can divide both numerator and denominator by 2, and that's going to give me 21 100ths. I don't think I need the two equal signs. And therefore, 42 out of 200 is the same as 21 out of 100, and therefore 21% of the vehicles fall in that most frequent category. All right, let's wrap this up. So today it was all about looking at data distribution shapes and some features of those shapes. For instance, we looked at a uniform distribution. That's when every sort of like possible data value occurs more or less the same number of times. A perfectly uniform data distribution, they'd all come in at exactly the same number of times, right? But assuming you don't have a uniform distribution, you can then have features like peaks in the data, i.e. where does the data spike up, how many, like a data point that occurs many, many, many times, like the mode. You can also have gaps in the data, places where particular data values never show up at all. All right. You can also have symmetric data sets. Those are data sets that look the same on the left as they do on the right. And again, the importance of symmetric data sets is that the mean and the median are basically the same when you have a symmetric data set. So therefore, you could use either measure when you've got that kind of situation going on. All right. Well, we're obviously going to see a variety of different data shapes as we move forward in statistics in our last few lessons. For now, I just want to thank you for joining me for another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.